Hello everyone, welcome to the lecture series on dynamics which is a part of engineering mechanics. In this lecture we are going to start the study of rectilinear motion. So in the earlier lecture we have discussed what is rectilinear motion and what are the features of that. Today we are going to derive some of the basic fundamental equations which are related to rectilinear motion. So in the earlier lecture we have said that the rectilinear motion means the particle which is moving along a straight line. So particle moving along a straight line is considered to be in a rectilinear motion. So when we consider the rectilinear motion, we know now that the object is going to travel along a straight line. So this will be the movement of the or motion of the particle either in the forward direction or in the backward direction. So right now for the simplicity of calculations, we are considering the forward direction as the positive one. This I am considering it as positive one, and left side as the negative one. Similarly, I am considering the upward as positive and downward as negative. And using these sign conventions, now we try to apply the basic fundamentals that are related to position, then displacement, velocity and acceleration. So first we try to understand what is the position and then we try to understand the displacement. Now to identify the position, first we have to define the origin and the line of motion. So I am considering this is the straight line along which the object is going to move, and I am considering the vertical line at this particular point, which is I am considering this direction as x direction and this as y direction, and the intersection of this is considered to be origin, whose ordinates will be 0, 0, x, y. Now suppose the object at any instant of time t. So when I say at any instant of time t, it means the moment I am starting the measurement of the motion. So suppose at any instant of time t, the object is somewhere here, and we'll consider this object is p, which is at a distance of x from the origin. Now if I take one part of this particular graph as 1 meter, then the position of this particular object will be 1, 2, 3, 4, 5, 6. So the object at any instant of time will have a position of xt, which is 6 meter. Similarly, if the object goes on the left hand side, so suppose the object will be at this particular point and it is traveling in the negative direction, because we have already said that rightward is positive, leftward is negative. So in the left direction, I will consider this object as q. Now the position of this particular object in the negative direction, I am considering it as, again I will consider as xq. So if again with the same principle, if I take 1 meter as one part of the graph, then 1, 2, 3, 4, 5, 6, 7, 8. So xt of q will be equal to minus 8 meter. So this is how you measure the position of any particular object at any instant of time. So using the same principle, we are trying to now measure the displacement. So as we have said in the earlier lecture, displacement is change in position. So first we have found out what is position, and now we are going to find out the displacement. So when I say displacement, I know that this is nothing new. Displacement is change in position. So that means the object will have certain initial position and certain final position. So if I take initial position as x0, final position as x. The initial position that I am measuring is at time t0, and the final position I am measuring is at time t. So what I'll do is I'll mark these positions on a graph so that it will be easier for us to understand. So I'll plot this graph. So suppose the object is initially somewhere here and later on it goes to this particular point. So I'll consider this as the P and this as P dash. So using again the same principle as we have discussed earlier, the initial position of this object I am considering it as x0, and the final position I am considering it as x. The time where I am considering the initial position as t and final position as t0 and final position as t. So now the difference between the initial and the final position that I am considering here is delta x. And similarly between the time periods I am considering this time period as delta t. So now when I want to calculate the displacement here, displacement I am going to represent it as s. S will be equals to change in position, so it will be final position minus initial position, and based on this I am going to get it as x minus x0, which is nothing but delta x. And as we have discussed earlier, this displacement s can be represented as dx. If I take the time period smaller, if I make the time from delta t to dt, which is time t tending towards 0. Now based on this we can find out the position, displacement. Now we will try to understand what is the earlier we have discussed the velocity. I'll just revise it and then we'll go to the further part. So second is velocity. Now the velocity, as we have discussed earlier, it is nothing but change in position with respect to time. And we have seen that V average is nothing but delta x upon delta t, or V instantaneous is nothing but dx by dt. For the calculation purpose we are considering V as dx by dt. Now last part is acceleration. So when I say acceleration, it is nothing but change in velocity with respect to time, which is nothing but acceleration will be, as discussed in the earlier lectures, it is dv by dt, or sometimes it is written as delta v by delta t, or we can write it as final velocity minus initial velocity divided by time. Now using these principles we will try to derive the basic equations which are required for the understanding of rectilinear motion, and we will try to get the equations of motion for the rectilinear motion. So using these same concepts and using some assumptions, what assumptions that we are going to do is, the first assumption that we are going to do is the acceleration is constant, and when the acceleration is constant we call that particular rectilinear motion as uniformly accelerated motion. Uniformly accelerated motion which is rectilinear. So this is a very important part of the syllabus. So when I say uniformly accelerated, that means what I am doing is I am considering the acceleration as constant. So when I say the acceleration is constant, that means the acceleration is not going to change throughout the motion. It is going to be same from the start to the end point. Now we are having some equations which are which we have derived earlier in the earlier part, which is nothing but we know that dx, which is change in position, which is x minus x0. Here I am considering x0 as the initial position, x as the final position, then I am writing this velocity as dx by dt and acceleration as dv by dt. Now if I have to make use of these equations, I can rewrite the acceleration as d by dt of v. Now I have the equation of v as this, which is d by dt of dx by dt, which I can write it as d2x divided by dt square. So this is again a very important equation that we have to consider. Now when I write the velocity as a function of time, and then what happens with the equations that we try to understand. So first is I am trying to rewrite the velocity as a function of time. So when I write the velocity as a function of time, I already know that acceleration can be defined as dv by dt. So I am writing the velocity as a function of time here. Now if I take this dt on the other side, it will be a into dt equals to dv. And now if I integrate this between the initial and final conditions, initial condition and final condition means initial conditions for velocity is initial conditions. So for velocity, I am considering v as the final velocity, which is the final condition, u as the initial velocity. Similarly for the time, t is the final time and t0 as initial time. Now if we integrate this equation within the limits of these initial and final conditions, what I get is integrating within the initial and final conditions, what I get is integration of a to dt. Now here the a is constant, as we have seen, acceleration is constant, so integration of dv. So the lower limit of here will be t0, upper limit will be t. In case of velocity, lower limit is u, upper limit is v. Now if I solve this, it will be a integration of dt, t0 to t, and this will be dv u to v. Now the integration of dt is t, and if I substitute the lower limit and upper limit, it will be t0 to t. Similarly, integration of v is dv is v. So initial limit is u, final limit is v. Now if I simplify this, what I will get is, a is missing. So if I solve this, what I will get, a multiplied by t minus t0, and it will be v minus u. Now if I start measuring the motion when the time t0 is equals to 0 seconds, then what will happen? It will be at, which is equals to v minus u, or I can write this as v equals to u plus at, which is very important equation in case of solution of particular problem. So this is the velocity in terms of time and acceleration. So time and acceleration. So whenever in a problem acceleration and time is given to you and they will ask you to either calculate the initial velocity or final velocity, you have to go with this equation. Then we'll try to write the position as a function of time. So second, position as a function of time. So when I write this, first we'll try to write the velocity equation, which will be position in terms of time. So velocity, I know v is equals to dx by dt. So again, I know that velocity, as we know, velocity is u plus at. So I'll substitute this equation of v in the equation. So I will write this as v into dt is equals to dx, or I can rewrite this as u plus at into dt is equals to dx. So now if I integrate this again within the initial and final limits, what I will get is initial limits for initial and final limits for position, as we have discussed earlier, x0 is the initial position and x is the final position. If you write this equation in terms of y, it will be y0 and y position. Time period, as we have discussed earlier, initial is t0 and final is t. So now again integrating this within the limits. So integrating within the limits, what I get is integration of u plus at into dt is equals to integration of dx. So lower limit for the time period is t0 to t, and here x0 to x. So if I simplify this, what I will get is integration of t0 to t u into dt plus integration of at into dt t0 to t is equals to integration of dx x0 to x. Now if I solve this, here the initial velocity is going to be constant, so it will be out of the integration, and the limits, if I solve integration of dt, will be t0 to t plus a is constant, integration of t is t square by 2. Again if I write t0 to t, and this will be integration of dx is x, so x minus x0. Sorry, if I x0 to x. Now substituting these values, what I will get, I will take this as t0 equals to 0. So I am starting from the 0 seconds. So what will happen? It will be ut plus at square by 2 is equals to x minus x0. So again if I rewrite, x is equals to x0 plus ut plus at square by 2, which is the equation of position with respect to time. So again this is very important equation for the solution of a particular problem. So this is one more equation which we have to remember. And the last equation that we'll try to understand is velocity as a function of position. So initially what we have discussed is velocity as a function of time and velocity displacement as a function of time. Now we'll try to understand velocity as a function of position, interdependent. Remember this, we have defined x in terms of t, v in terms of t, and now we are going to define v and x in terms of each other. See, we are not taking a in terms of any time or position because it is a constant parameter. So you cannot define it in terms of any other parameter because it is a constant, it is not going to change. So last one is velocity as a function of position. Velocity as a function of position. So here what we'll do is, first we'll try to write the equation of acceleration, which is a equals to dv by dt, and we know that v equals to dx by dt. Now if I write the value of dt as dx divided by v, and if I substitute this value of equation here, what I will get is a is equals to dv divided by, in terms of dt it becomes dx by v. So now if I simplify this, what I will get is a into dx divided by v equals to dv, or I can write this as a into dx is equals to v into dv. Now if I again integrate this within the initial and final limits, as we have discussed earlier, initial limits for position x0 and x, and for velocity it is u and v. So integrating this, within the limits, what I get is integration of a into dx, x0 into x is equals to integration of v into dv u to v. Now since the acceleration is constant, it will be out of the integration, and integration of dx will be x, so it will be x, lower limit will be x0, upper limit will be x. Similarly, integration of v into dv will be v square divided by 2, lower limit will be u, upper limit will be v. So now if I substitute these values, it will be a into x minus x0, and this will be, if I take half of the equation out of the equation, then it will be v square minus u square. Now if I solve this, what I will get is v square minus u square, half I am taking on the other side here, so it will be equal to 2ax minus x0, or I can write this as v square is equal to u square, or I'll take this u square at the end, so it will be 2ax minus x0 plus u square, or you can remember this as v square minus u square is equals to 2ax minus x0. So this is the equation of velocity as a function of position. So in the equation, if they have given you the position and they have asked you to calculate the velocities, or they have given you the velocities and asked you to calculate the positions, you have to go with this equation, which is very, very important for the problem solving. So using these equations, there are some questions that will be asked in the exam. We'll try to simplify and solve those equations or those problems. So we'll try to solve the questions from the D/2 question papers itself, so that it will be easier for us to understand the problems.